Nuclear forces. Why don't protons explode? After all, positive electric charges repel each other. Positive charges push away each other, and negative charges repulse each other. If they repel each other, just like repel repels mosquitoes. Yes! Strong force to the rescue. Strong nuclear forces. It's an extremely strong force that acts against the electromagnetic force repelling protons in the nucleus. The strong nuclear force is very short-ranged. It's one of the four basic forces in nature. Oh, what? You don't remember the four basic forces in nature? Well, let's review those four basic forces in nature. So the four basic forces in nature: gravity, very long range, works on mass. It's the weakest of the forces, and it's attraction only. Electromagnetic force. It is a long range force. You're familiar with this one also. Electrically charged, it repels and attracts. Repel and attract. You experience that when you have a magnet. That's the force you're talking about here, electromagnetism. It's also called an electric force. It's where the protons are repulsed by other protons because they're both positively charged. However, the protons like the electrons because they're negatively charged, and the protons' positive charge are attracted to each other. So that's where the attraction and the repulsion is when like repels like. That means positive charges don't like being around positive charges, and negative charges don't like being around other negative charges. Then there's the weak nuclear force. It's short range, causes beta decay. We don't really get into it in this course. And then there's the strong nuclear force. It's short range though. It's very strong but short range. And it's an attractive force. That means that protons and neutrons are attracted to each other, but only about the distance of one proton from each other. So it's very, very short range. Electromagnetism, your experience with that, that's over distance and sometimes over a large distance. Whereas gravity, you're familiar with its long range over very, very long range, like from the planets to the stars. Here's a visual example. Go ahead and stop and copy this down if you'd like that. You like the visual reminders. There's a strong force which binds together the nucleus. Electromagnetic force binds atoms. Though on atoms, that's more that it combines two atoms together. The electrons are what causes molecules to form. That's a combination of two or more atoms. That is through the electrons. Then there's the weak force that's involved in radioactive decay. And then gravitational force. That's the huge one that binds the solar system together. So let's see how much you paid attention to that last slide. Which force is responsible for a neutron decaying into a proton? Go ahead and pause and think about it a minute. Weak force. Which force bonds quarks together into particles like protons and neutrons? Da, 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 da. Strong force. Which force governs the motion of an apple falling from a tree? Gravity. And what forces hold you together? Electromagnetism. The electromagnetic force, just to give you a little background information on it, is long ranged. Like repels like. You can see over here, positive charges are repulsed. Also negative charges, they're the same, they're repulsed. However, if it's a positive and a negative, they're opposite charges, then they attract. And notice it only works on charges. It does not work if there's no charge involved. It is within the nucleus, because the protons have a positive charge, it causes the protons to repel each other. Neutrons do not have a charge, so the electromagnetic force does not work on neutrons. So back to our strong force, the one that's extremely strong, however very short range, basic force in nature. So only those that are very, very close you could say within touching range, are the ones that act on the strong force. Strong but short-ranged. Only strong within about 1 proton-sized radius. Short range, but stronger than the electromagnetic force in the area that it operates in. This is the force that causes the nucleus to stay together. You see where the strong force is working on the protons, they're attracted to each other. So electrical force is kind of wimpy, but it works over a longer range. In this case, the total force is it stays together. The nucleus stays together because the strong force is overcoming the electromagnetic force. However, if you separate these, like let's say you're in a nucleus and you may have a lot of neutrons here separating them. It's a very big, very big. Well, you no longer have that one touching that one, so there's no strong force coming into play here. So the strong force is 0. The electrical force operates because this is still operating. Remember I said how electrical force is a longer ranged force? It's still operating, and so the total force is saying separate. Too far apart for strong force. The electrical force causes the nucleus to separate. We call that decay. So which force wins? Well, you have to see how close together they are. It's a constant struggle between the strong force and the electrical force. It's dependent on the number of protons and the number of neutrons. Neutrons, if you'll recall, don't add to the electrical force, the electromagnetic force. Neutrons don't have a charge, so they don't repel or attract. However, in the strong force, it's dependent on protons and neutrons. It's not dependent on a charge. So if you have more neutrons than protons, the protons are trying to push away, but the neutrons are trying to hold everything together. So which force wins? It depends on the size of your nucleus. You look at the forces acting upon the proton. So we're looking at this one proton. This one is saying stay, this one is saying stay, this one is saying stay. So everything around here is saying stay. Now these other things, it's saying stay, but yet at the same time the electromagnetic force is saying go away. So it's saying go away. It's saying go away. But at the same time it's also saying stay because it's close proximity. So you have 1, 2, 3, 4, 5, 6, 7, 8 saying stay, and you have 1, 2, 3 saying go away. I'm going to show an arrow meaning go away, and a short one saying stay, stay. So in this case, what are the strong forces? We've identified that. There's about 8 of them. What are the electric forces? We've identified that. That's 3. The 3 is outnumbered by the 8, so it's going to stay together. Now let's look at another example. How does this differ from the previous slide? Well, look at it. What's the difference? It has more. It has more neutrons and it has more protons. So let's see what are the strong forces acting on this one particular proton. This one particular proton has stay with me, stay with me, stay with me. So it has 1, 2, 3, 4, 5, 6. That might be too far away, but we'll count it. We'll be nice. So we'll say it has 7 saying stay with me, stay with me. But remember, it's only short focus. Now let's count the ones saying go away. This one is saying go away. This one is saying go away. This one is saying go away. So let's count all these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So at least 26, and there's lots more underneath that we're not counting. But you get the general idea that there's 26 saying go away. So for a large nucleus, you have many more protons saying go away than you have neutrons and protons within touching distance that say stay. So in these cases, the electrical forces wins, and generally the atomic nuclei is torn apart. And that's what causes radioactivity. When the electromagnetic repulsive force overcomes the strong nuclear force. Elements with smaller nuclei are more stable, as we saw in the previous example. Whereas large elements have more neutrons and protons are also more stable than large elements that have the same number. Neutrons still have the strong force saying, stay with me, but they don't have the electrical repulsive force that say, go away, you smell. So I'd like you to do the rest of this time as we have a few self-checks here. Describe the properties of the strong force. Go ahead and pause and think about it if you need to. So some properties, it's short-ranged, strong force, and go review your notes to find the other one. Another self-check, compare the strong force between protons and neutrons in a small nucleus and an atom with a large nucleus. And does this explain why large nuclei are unstable? Aren't they unstable because there's so many electromagnetic forces acting on it, but only a few saying, stay with me? And then last, I'd like you to explain why the number of neutrons to protons ratio makes a difference. And I hope you enjoyed this little video on strong forces. Enjoy.